All right, so we're looking at this study guide. So if you go back to this unit, what we've been talking about is projectiles and how things move through the air, right? So the first piece is when we went to the commons and we were doing the ball toss, right? And we were showing that horizontal motion and vertical motion are independent, right? That they don't affect each other. From there, we were talking about, and there were some problems we did that talked about that. Then we went into the hang time and the maximum height and the range using the different equations that you see here. And we did a number of problems with those guys. Remember, if you were in those problems, you were given the initial velocity and you had to find its components, right? Because it was going both up and over. So we had to break it into the two pieces. And for the hang time and the maximum height, you would use the y component of that velocity. For the range, you would use the x component of that velocity. We did some work with centripetal acceleration, where you were spinning your payloads, right? Why did we do this? Like I wrote up there how it relates to our rockets. How does this centripetal acceleration deal with what we are doing in our rockets? How did we use it? Okay, we're creating acceleration, testing g-force, right? So it was an easy way, I mean not that easy, but it was a way for us to put our payloads under acceleration, right? Which would then add the forces onto them with the mass that they have. So that was one thing that we could do. The equation we used for that, to calculate that, because basically acceleration of centripetal acceleration is velocity squared times radius. And we had to just figure out what was the velocity. And we did that by taking the distance around, right? The circumference of the circle. So we had to measure how far that r was, and that was the big thing we tried to find, right? We tried to solve for r, so we could figure out how long did my rope have to be in order to get certain amounts of g's, right? And then the third set of problems we did was talking about range, if you only knew the angle and the time, right? So we used this formula, right? The cosine of theta times g times t squared divided by the sine of theta times 2. So if I only knew, if all I had was the angle the rocket was launched at or the ball was thrown at and how long it was in the air, I could find its range, right? And the last piece that we're doing today, is and as well as we started on Monday, is this aerodynamic drag. The pieces that were affecting that, and I'm going to introduce you to this equation for drag today that puts these three pieces together into a formula. Terminal velocity will come into that as well. We'll mention that as well as how it relates to drag. Does this make sense? Any questions? Again, we haven't talked about all the drag stuff. We'll talk about that today. Are there other questions about the pieces here? Again, on Schoology are all the problems that we've done, all the answers that we've done, all those pieces are all up there for you. So do make sure you're comfortable with how we do those. So again, the centripetal acceleration is, the definition is like center-seeking acceleration. It's that acceleration that's moving something in a circle, right? And how it related to our rockets was we used it, because our rockets aren't undergoing centripetal acceleration. It's all just straight line acceleration, because centripetal is curved. Matt, you don't want lunch, do you? So how it relates to our rockets is we use centripetal acceleration to simulate that straight line acceleration that we would receive, again, when the rocket blasts off or when it hits the ground. But we can't blast it off yet. Well, only when we go take our rockets. So just a way for us to test that. All right, so let's talk about our three pieces that we spent some time with on Monday, as well as you spent a little bit of time yesterday. I did get some more good things from you yesterday, and I appreciate that. I'll change the date on that so it won't be late for you. I need some definitions, though. Can somebody help me out? When we're talking about air density, what do we mean? Somebody from that group, or a couple of you from that group, what are we talking about when we say air density? And again, going back, we're looking at drag, right? In all the problems we've done so far, we've ignored air resistance, right? But now if we want to actually start to calculate that, we need to know about these three things. About air density, about the surface area of our rocket, and the drag coefficient on the body of the rocket. So let's talk about air density. Give me a raised hand. Those of you who are someone who was in that group, or a couple of you from that group, what do we mean when we're talking about air density? You guys look tired. Must have been a busy day yesterday. I'm tired too, I must admit. Nobody? The density of the air, good, okay. Density is mass over volume, right? So we're talking about basically how thick the air is, right? Okay, what is that, what affects that density? What kind of things affect that? Yes? Okay, humidity, temperature, altitude. Anything else you all would put there? Well, that's a pretty solid pieces, right? Now, what's interesting was in my research, I didn't find a lot that you would easily calculate the humidity piece. Temperature and altitude was an easy one to find. If you were to do some searching, you can easily get charts like this that are looking at certain altitudes, right? And they're basically just making temperature a function of the altitude. What would the density of the air be? And density is symbolized by this kind of P-looking thing like this. It's a rho. It's a Greek letter. And that's what they use for the density of the air. Now the units here are in slugs per cubic foot. And slug is another way that we measure mass. If you want to see it in the units that you and I would use, because again we're using SI units, we would roll down here, and you now have density as a function of kilograms over meters cubed, which that's what we want, right? Mass over volume. That's what density is. Remember back to chemistry. Mass over volume. That's what density is. So, what do you see? Just taking a quick look here. As the altitude is increasing, what's happening to our density? Significantly decreasing, right? Which makes sense, right? More air down here with us, less air the further up we go, right? So it would actually be a bit of a sliding scale. Now our rockets are probably only going to get up in this range, 5,000 to 6,000 feet. But there's definitely a difference, right? At 6,000 feet, the density is 6.601. By the way, if you look at the units, it's 10 to the negative 1. So it's actually 0.6601. So don't miss that. And here, it is 1.225, right? So we're about half. From the top of our to the bottom, we've lost about half of our air density. Does that make sense? Sir? There's just actually less air particles. So actually the mass is really what's changing. Like we're still taking about the same amount of volume of air, it just has less air particles. Think about if I were to take you right now up to the top of Mount Everest, right? Would you be able to breathe? No, you would die within a couple of minutes. Even though there's still oxygen there, the air is so much less dense. Does that make sense? Have you all heard of this before? Okay, I'm just making sure I'm not just tossing you things you don't know. But that is true. Because we're at about sea level here. We're maybe a couple hundred feet up, if that, where we are here in Spencerville. If I were to take you to Mount Everest, right, over 20,000 feet up, right? I mean, there would be some problems. Now this is in meters, so you'd be about 10,000 meters. Are we cool? All right. Does that make sense what we're looking at air density-wise? So the number we're going to pick is basically just this sea level density, right? Because we're going to be shooting over on the eastern shore. It's pretty much going to be at sea level. We may be up, not even less height than we are here, maybe 50 or 60 feet up in the air. but not enough to significantly affect that piece. The temperature they picked here is 15 degrees Celsius. We're going to be a little bit colder than that. It is February. 15 degrees is probably in the 50s Fahrenheit-wise. 15 degrees Celsius, we about in the 50s Fahrenheit-wise. So it'll actually be probably even a little bit less than that, because of course the colder you get, the less dense the air is. Does that make sense? Because the particles aren't moving as fast. They slow down. So there's less collisions between the rocket and the particles, and so less force put on there. We cool so far? All right, let's go back to our list. How about surface area? How do we calculate surface area for this guy? Again, I saw some good answers for this one. Yes, sir? Okay, okay. Keep going. Okay, okay. So, he's speaking of, as I grab the rocket here, he's speaking of like actually taking each piece of this, right? So here's a cone, or a triangle even, right? Here's a rectangle, and then we can break these into their shapes, right? And you can actually calculate the surface area that way. Now let me ask you this. As the rocket is moving through the air, how is it moving? Does that make sense? It's going this way, right? If I point the nose at you, it's going this way, right? So the surface area that's mostly being affected, is it the lateral side of it? No, it's more the front side of it, right? So in actuality, like what shape are we dealing with? Just a circle, right? Now we're simplifying because we've got a little bit of the fins, right? So we could add a little bit more surface area there as well. But the easiest way is to think of this as a circle, right? And that's how most of the modeling that they do, unless you're getting into the significant, in-depth, precise modeling, we just kind of ignore these guys. We assume that we've beveled these and made them nice and thin enough that there's very little bit of air resistance is affecting there. Does that make sense? So how would I find the surface area of the rocket if we're just talking about the circle in the front? Sorry? Pi r squared, right? I just find the area of a circle, which of course you all know is pi r squared. So I got two terms already, right? I've got a number for air density that we found using that chart. We can use pi r squared to find the surface area of a rocket. Okay, how about the drag coefficient? What did you guys find out about that? Anybody? All right. Well, let me say this. What do you think drag coefficient is based on? Okay, the shape and? Okay, certainly velocity plays a big role in that. You'll see that in the equation we pop up there. What else? Okay, sure, so all three of these work together. You're right. In our drag formula, all three of these will be present. But I want to just focus only on the drag coefficient. There was actually one, I don't remember who it was, who actually had the formula for drag, and they had solved it around to find for the drag coefficient, which is cool. But I want to just pull out that one drag coefficient piece. What do you think would affect it? Think about what we spent a bunch of time doing to the rocket after you glued the fins on. Yeah, so what do we do to the epoxy on the fins? We sanded it. What did we do to the rocket body itself? There was some sanding that was done, right, to make sure it was nice and smooth, right? Because the surface, like how it is, the smoothness of it, the material it's made out of, those kinds of things will affect how the air flows on the rocket. Does that make sense? So right, it does definitely come back to surface area. It comes back to all those pieces. It also is like, what is the rocket body made out of? You know, they try and make it out of nice, slippery least amount of friction kind of material. They don't want, you know, a nice sticky rubber on the outside. Does that make sense? Because you have to think of air like a fluid, like water, that's literally rolling over and moving over this rocket. You want it to be as nice and smooth and flat as possible. Does that make sense? So these two are definitely related. I'm sorry, all three of them are definitely related. And the drag coefficient in particular is definitely related to that. So there's a couple of ways we can go about finding this. If you just search drag coefficient, they put you in a bunch of different shapes. What is the drag coefficient? And by the way, they abbreviate that as CD, the coefficient of drag, right? It's a unitless number. It's just simply a ratio. The same thing when we measure friction. We can actually determine, like, this surface, how much friction is there. There's not a lot. Versus this floor, there's more friction there. Oh, that's terrible. Are you with me? And there's no units there. It's just a ratio. And we can roll through. And there's lots of different pieces. You want to know, like, for specific car types, here's their coefficient of drag. Why does that, like, who cares about that? Why is that important? Yeah, absolutely. The less drag you have, the less the air is slowing you down as you're working. So if your engine's producing the same amount of power, if I have less drag, I go faster, right? More drag, I go slower. So obviously a race car wants to be as little drag as possible. Yeah, who cares about building? Why would the coefficient of drag play a role in like, why would you want to know that about a building? Absolutely. There's forces that are involved with that wind hitting the building. And again, the wind acts just like a fluid. It literally rolls right up the sides of buildings. And the amount of drag between the materials there will absolutely depend. Have you ever been in a tall building and felt it shake from the wind? Oh, that's very cool, I think. That's very cool. The Sears Tower, or it's the Willis Tower, I guess, now in Chicago. That's always what I think of. Because Chicago's a very windy city, right? That's like the nickname for it. And I've stood on top of that building, and like you can literally watch it do this. And it's moving a good couple of feet. It's not like just little tiny movements. You can really feel it. But that's how the building is designed. It's actually designed to do that. Why? Holding still actually takes more force than letting it move. And the building is just actually built to allow that bit of sway. That's kind of cool. All right? So you can look through all of these here. Do you see this right here? A typical model rocket. Here's our drag number. About 0.75. Are you with me, my friends? So if I take and I put all those guys together, the equation that I end up with, and I'll pop this up. This is, Brian made this up, and I'll put it up for you. Our equation we end up with is this. That drag equals 1/2 times the atmospheric density, which again is called rho, or that P symbol, times the square of velocity. So you see, the faster you go, the more drag you get. And it's not just a little bit more, it's a squared relationship. Does that make sense? So if I'm going, let's say, 40 miles an hour versus 50 miles an hour, right? It's a significant increase in the amount of drag we're talking about, because it's 40 squared and 50 squared. Does that make sense? Okay. 180 versus 250, right? Significant differences. Oh, sorry, add another 0 on the back of those guys. We cool? So drag 1/2 times rho times v squared times that drag coefficient. For your rockets, again, 0.75 is about what we're dealing with there. Times the aerodynamic reference area. In other words, the surface area. And that's simply how we calculate drag. 0.5 times rho times v squared times CD times the area of reference. All right, so let's do some calculating. Let's move this down here. So how do we find that again? Drag is equal to 0.5 times what? Rho, so I'm just going to make that little P symbol, right? Times velocity squared times the coefficient of drag, right? Times the area, the surface area. Well, I better use A because that's acceleration. So the surface area. Okay. What was the atmospheric piece that we had? I really shouldn't make it a P. I should make it like this. What did we say that was? Do you remember? What's that? It's close. Right, right. Again, we're going to use our units here. Now remember, these are 10 to the negative 1 units. So I have to actually move this decimal over one place to the left. So at sea level, it'll be 1.225. Sure. Yeah. So in actuality, and if you remember what Mr. Kuzma did with his Excel spreadsheet, the number would change depending on your altitude. Does that make sense? But we're just going to calculate it for right here. So we'd have to continue to calculate those drags for every change in your altitude. You're absolutely correct, because it would change as we go. We could calculate it once here and then once like up at 5,000 feet and see what the difference would be. Yeah, it's good. Yes, Joyce? Sorry? The units for this is kilogram over meters cubed. Because if you remember, density is mass over volume, and volume is meters times meters times meters. Height times width times base. Base times width times height. There we go. Make sense? Okay. Okay, sorry, what was my number again? 1.225. Okay, and again, that's kilograms per meters cubed. Our velocity is a question mark, because right now we don't really know what that would be. Okay? How about if we just make a guess that we're going at 125 meters per second? We'll go with that, and we can change that. What was my coefficient of drag? Okay? And then my surface area. Yep. Sorry, that was from this chart that we looked at. That we're just using this typical model rocket drag. And then how would I find my surface area? What's my, again, we're looking at just a circle, right? So it's pi r squared. Okay, so pi r squared. The diameter of your rocket I measured is 0.79 centimeters. All right? Like from one end to the other. Across, I took off the nose cone and measured that body of the rocket. So how would that be in meters? How many meters would that be? We're testing you. How many centimeters in a meter? 100. So I divide that number by 100, right? So 0.079. Good. If it was just 0.79, that'd just be that they were decameters. Or decimeters, not deca, deci. Okay? So I'm taking the area to be pi times, if I want to find r, how do I get r from diameter? Is what? Good, good, good. So 0.5 times 0.079, and I'm going to square that. So can somebody pop that in for me? What do I get? Hello, is Nathan? Not here. Not here. Here, yes. Thank you. So we got a number? $0.124. Oh. What you got, Joyce? 0.00156. Yes, no, maybe so? What are my units? Not just meters. Meters squared. Because area, right? Height times width, right? Okay. So I can plug these in now, right? Good. Can we do that? Will you try that for me? Pop it into our drag formula. Let's see what we got. Right. Times velocity squared. That's supposed to be a times. What do you got, Joyce? You need help? Oh, okay. Because the area I got calculating is 0.00490. Yeah. So that would be a change. So let's put that up there. What was that number again? 0.00? Okay. Yes. Sorry if you've already started calculating how to redo that piece. My apologies. It's difficult if you're using this guy. Because you have to make sure you do the right operations, like the order of it. So, good, yeah. Yep. The meter squared is just a unit. Velocity up there is a squared on the formula. Yeah. Somebody have a number? 35.17. I'm looking for some confirmation. Yeah? 35.17? Okay. My question to you is this. What units would this drag be in? Okay. Yeah, you're right. There's actually a simpler way we could say it, though. I'll give you a hint. It's kilograms times meters per second squared. What's that? It's not a negative velocity. But that's you said velocity. Now you said not acceleration. Not close to impulse. It's a force. And again, I'm being picky because all those words mean different things. Right? An impulse is a force over time. Right? Acceleration is a change in velocity over time. Does that make sense? Velocity is a change of distance over time. So it's a force. So what units do we use for force? Newtons. So there's my drag, 35.17 newtons. Does that make sense, my friends?
You said the drag is not really specified unit.
No, it's unitless.
Okay, so it's not always going to be unit.
It won't always be 0.75. Sorry, the coefficient of drag, the CD, is always unitless. The drag is always a force. It's always a force. It'll always be, for our purposes, because we're doing SI units, yes, it'll always be in newtons. Right, because if you used English units, yeah, I'll put up Brian's piece, and he did all of it in English units. Like when he did his work, I have to scroll down here to see that, but he did it all in English units. So it looks totally different. That's where he used these slugs. He used feet per second squared instead of meters per second squared.
But it doesn't matter what application you use.
Exactly, for drag coefficient. I will have a couple of problems up on Schoology. I want you to check them out and give them a shot for tomorrow. Just a couple, 2 or 3. Okay? Adios, friends.